Thank you.
Thank you, Maria, for this kind introduction, and thank you to the organizer, Maria, and you, Paula, for inviting me to this data science and statistic webinar. It's a pleasure, always a pleasure to give a webinar to well-known colleagues and some unknown colleagues. It is a pleasure to meet you. Of course, I hope the next time it will be in presence somewhere in Portugal, but for now it's just by Zoom. So I've after your invitation, I've just think about the topic I would choose for this the webinar. So I've chosen something which is a joint work with some colleague from different point of research. Matthias Burrell, which is in Montevideo in Uruguay, Jairo Gugliari from Lyon in France, Yannick Good from EDF, which is a French electrical company, and myself. And the topic I've chosen is boosting diversity in regression ensembles. And in fact, it is something bridging a well-known machine learning technique, boosting, with something which is quite interesting from something I discovered some years ago. I just ignored the aspect of diversity, and so I have chosen to start with some kind of motivation about diversity. So with these three colleagues, we are interested in combining experts. So you imagine that you have something which is like this equation. I hope that you see by slide number 2 now. So you have y of t denote the time. It is a function of f, a function f, which is quite arbitrary, nonlinear, whatever you want. A function of a covariate xt, which could be some lagged value of y, plus some derivation, and then you consider different individual predictor. That is some quantity, some algorithm, f1, f2, f capital M, generating some prediction about the future value of y. So each individual predictor delivers some prediction of the next value of y. And instead of considering, as usual in statistics, a way to choose the best one or some interesting one, in this kind of strategy, you consider something which is the aggregated predictor. So you choose a weighted mean by choosing this coefficient. Of course, this beautiful theory of sequential learning allows you to choose in a clever way the weights C of M, but it's not my point here. Suppose that you have some way to combine this different prediction, and instead of choosing one of them, you just predict by the weighted average value. So the aggregated estimate is just this formula. And what is interesting is that when you consider the squared error, the difference between the y value and the predicted value, that is the one which is given by the aggregated predictor written here. So you have here just a difference. There is no expectation, no sum, nothing. You just consider the instantaneous error, and then you just decompose this. And there is a well-known identity due to people, we get back to the last century. You can find very interesting insight about diversity in many papers by Brown. And the idea is to analyze the ensemble aggregation through the decomposition of the mean square error in terms of diversity. And if you do that, if you decompose this, you can prove that this instantaneous error is the difference between two terms. The first one in blue is simply the weighted average of the individual error. That is the square error of the square difference between the prediction given by expert number M and the value of the measure. This is the error of the mth predictor. And this is just the weighted average error of this prediction. And the second term is something which is called the diversity term. That is the way in which each individual predictor differ from this aggregated one. So it is in terms of diversity because this is large when the different FM differ from the mean value. So what is remarkable, it is a positive term, which is the difference between two positive terms. So, for example, if you consider a given set of experts, and then you try to combine this expert in the best way, the question could be how to increase the diversity of the set in order to improve the performance of the aggregated predictor. So if you imagine that you have a mechanism which produce some predictor which are relatively accurate in order to preserve that this term is not too large. The increase is moderate, and if you generate diverse predictor in certain sense, you can reduce the error at the end of the day. So this is quite a surprising result. And in fact, this is incorporated in many different machine learning algorithm. And the topic of this talk is just to take a very well-known algorithm, which is boosting, and considering boosting in the L2 sense, that you just consider mean square error, and you just want to incorporate in the usual boosting algorithm some diversity term, and just inspect what happens. So this is the topic of my talk. So the idea is we will start by the L2 gradient boosting algorithm. We take exactly the same as nonlinear aggregation I have broadly introduced crudely introduced in the last slide, which is due mainly to Friedman. You imagine that Friedman is one of the main scientists making the connection between the Freud-Shapiro formulation of the initial boosting algorithm in the binary classification case and moving to a very elegant formulation in terms of gradient boosting. So I just take this in the regression problem in the L2 gradient boosting. And some other main contribution is the paper from Bullman and Yu about the L2 gradient. And we just propose to modify the cost function, the usual cost function for the L2 boosting is just this one, the mean square error. And the idea is to incorporate in this cost function some additional terms in order to enhance diversity during the learning iteration, generating the individual experts. So in this formula, F bar is seen as a constant, but of course in practice, it is the mean of the past individual predictors produced by the learning steps. And of course, you have a parameter, which is a kappa, is +1, which in fact allows you to tune the diversity. You can tune the importance given to the diversity in the iteration of the boosting. So for those of you which are not familiar with boosting, I just spent some time to just show you this slide precisely. So in fact, I will take some minutes to just comment in details these different steps, but just to have a big picture, if you just avoid to look at the parts which are in orange, this is the classical L2 boosting. And then the addendum we have made is just the aspect which are in orange. So the kappa here is the one you have here. If you increase kappa, you increase the diversity in the sequence of boosting algorithm. And this is the term which is a consequence of the change of the cost function by hiding this diversity term. So now I just start the comment by focusing only on the blue aspect. So my first reading is just describing you, recording you what is L2 boosting. So you have a learning sample, Y, X, so you have complete observation, you have X and Y for a sample of size N. You have a family of function that, let's say that this is, for example, the family of, this is the function you will use to estimate the underlying F regression function. So, for example, you could have in mind that this could be a regression tree or a random forest or something like that. Your tree-based method that are well used in this kind of context. I will use repeatedly this kind of thing in the SEQL. Delta is the gain, the small value of the gain introduced by classical boosting. I will just comment this on that. And you randomly split the data into two parts. This is not crucial at this stage. And the first step is quite simple. You take your data and you take your favorite method, for example, a cart decision tree, and then you fit in the mean square sense, you fit a good model for your data, and then you obtain the first value of the additive formulation of the final estimation. So the idea is to give an estimate of the unknown regression function f, and then we will the boosting deliver some additive formulation of such an algorithm. And the first step is just you fit your favorite method on your data. This is the first initial learner. And then you have now the loop. And the loop in the gradient boosting, you just consider the residuals. So instead of considering your data, you just consider now the residual between your measure and your current value of your estimation of the f function. So you have your residual, and again, you fit your favorite using your favorite method, the same one as previously. For example, the cart decision tree, and you obtain f hat 1, which is the best way to model the residual. And then you update the boosting predictor. So this is the additive formulation. That is the estimator step M is the one at the previous step, plus something which is a piece of the new estimator. So this is the delta, which is here. In general, this delta is quite small. For example, 0.05 or something like that. It is quite close to 0. And you have now something which is f hat, and you have something which is a crude version. It is f hat star, which is just the mean value of the f hat. So this is not crucial. You can focus on the boosting predictor, and then you continue this loop. So you take now the residual you obtain between the measure and your current estimate, and then you iterate in many steps. And at the end of the day, you have capital M steps, and then we consider the family of individual expert, small f, f1, f2, f capital M, and some aggregated expert, the usual one, f hat of M, which is the usual boosting estimate, and this one, which is some crude average value of the estimate. So this is boosting. In fact, if you take kappa equal to 0, you get the L2 gradient boosting. And now what we propose is just to incorporate kappa in this scheme. So we set a value of kappa which is positive, and we compute. So the residual is in fact the negative gradient of the cost function, which is here. As you probably know, in the first course of L2 gradient boosting, the first thing is just to show that, in fact, the residual is much more interesting than the residual. It is, in fact, the gradient of the cost function. So instead of taking the negative gradient of the cost function of the mean square, you just take this one, this augmented cost function, and then you get this formulation. So the negative diversity gradient of the cost function is of this form. The first term is exactly the same as in the boosting case, corresponding to kappa equal to 0, and something which is a difference between the current estimates and something which is the mean value of the estimate. It is now something reminiscent to you. This is the counterpart of the term, which is in fact here denoted by F bar. And then nothing is changed at the end of this. So you have just add one new parameter. It is kappa, how to choose kappa, but everything, every trick you have, every way to manage boosting, your own experience about tuning parameters, selecting the number of steps, selecting delta, everything could be, of course, used in the same manner. You just have to inspect what is the role of kappa and what is the influence of kappa. So my talk will be focused on this in quite descriptive way, just after mentioning a theoretical result that you can extremely in a very easy way have a first result about some kind of theoretical guarantee that if kappa is non-negative and kappa is less to 1, then the new cost function is strongly convex and Lipschitz, and in fact you you can use a very general result of a beautiful paper written by Bio and Cadre about very general result about gradient boosting in Riemannian and in very, very abstract framework. You can, quite just checking the condition, have the following theorem. So on a condition on delta, then the optimization strategy converges to a global minimum in the sense that the limit when t goes to infinity, that is the number of steps of the algorithm goes to infinity, the expectation of the cost is reaching infimum, where this lin f denotes the linear span of the family of function. Typically, you could consider the collection of all card trees with a given number of terminal nodes. So this is an optimization result. It is not a statistical one, but it gives you some kind of you have no information about the rate of convergence and so on, but you have some kind of guarantee on your algorithm. Okay, so now I propose to dive into experiments. And starting with a very, very simple example due to Friedman. It's a simulated data set, which was used by Breman in his paper introducing bagging in the middle of 90s. So this is a regression equation involving 10 independent variables, but only 5 are active in this formula. Y of I are only a function of the first 5 x values. So you have 2 linear terms and 2 nonlinear terms involving the 3 first variables. So I don't want to discuss this model. It is nonlinear model, classical in this kind of, this example has been used a lot of times. So we just propose to take the framework used by Breman in his paper. And what is very interesting is that which kind of Bayes learner, that is, I just say to you that we could consider in the algorithm that this f, this is a family of function you use to approximate regression function. What is the method you want to use? So we propose here to use 3 different Bayes learner, which are all based on trees. So I suppose that everyone know what is a regression trees. If there is someone which is not familiar at all with this kind of thing, I can just say a few words, but without any request of this nature, I could consider that everyone know it is really a basic model and quite not successful, even if one tree is not really a good idea. A combination of tree, a set of tree, using bagging, using random forest, could be very promising. So it is a very simple way to control the complexity and the diversibility. It is also to control the depth of the tree. So this explains why in many machine learning studies, everyone considers some tree-based method to calibrate the method. So here we consider 3 different tree-based methods. The first one is very simple card trees. It is stumps. There's a card trees with only 1 split. So this is something which is you try to approximate the regression function only by a piecewise constant function with only 1 separation. So 2 constant, and you have to select the 2 constant and the frontier. So this is a very simple model. which was used a lot of times from theoretical, in particular in the paper of Bullman and Yu. And we take two types of random forest. The first one is the famous Breimann random forest. So including some perturbation when you take card trees. I recall that Breimann introduced two kinds of perturbation. The first one is the one introduced in the bagging, that is resampling the observation. And the second one is at each node, when you select the best split, you just try to incorporate a new additional randomness by selecting the best split, not among all the splits, but all the split based on a subset of randomly chosen input variable. So this is the Breimann strategy. But of course, you have many different schemes of random forest. And one which could be very interesting is a poorly random variant. So it is just denoted here PRF. It is the idea of choosing randomly the variable and the value of cut, the value of split. You choose everything randomly. So you generate some kind of random partition, and the final random forest is just a regressogram on a poorly random. So you disconnect the dependence of the partition in the explanatory space from the data. Okay, so it is a variant which is used a lot of time from theoretical region, but it appears that from practical point of view, it is quite interesting. But what about diversity? Why we have chosen this? So we want to have some kind of gradation. You have stump, which is very simple. You have card trees, which is much more sophisticated, random forest, and something which seems to be intuitively more diversifiable, because you could imagine then PRF could give you some additional interest in terms of diversity. So I just now show you some example. The first thing is we could just have a first graph to inspect the influence of the diversity weight, that is the kappa, and the gradient step, the delta algorithm. So you have here in this plot, in abscissa, in x-axis you have m, which is the number of steps of the boosting algorithm, and in the y-axis you have the mean square error. So in green you have different value of kappa. So in green, sorry, in green, blue, and red you have different value of kappa, and you have dotted or solid line for different value of delta. So for delta, it is not really an issue. You have something which is quite close to what you have in mind for delta in classical boosting. But what is interesting here is that you can see that kappa equal to 0 is the case of boosting. So you can see that when you increase the value of kappa, the results are better. So this illustrates the fact that it is quite interesting to encourage diversity in the algorithm. At the end of the day, you get better results. This is the example for purely random forest based predictor. So now we could just have a look at the difference for with respect to the Bayes predictor you use, the Bayes learner. So in this graph, you have exactly in x and x-axis and y-axis exactly the same quantity, and you have the evolution of the mean square error of the aggregated predictor at f and f star. I just recall you that capital F is simply the usual iteration of boosting. So the additive formulation of your estimator, and F star is the mean value of this instantaneous approximation. And we can inspect this with respect to the three Bayes learner. We have in red the stumps, so you can see that the value is quite high. The purely random forest in blue and the random forest in green. So we reached the best result for random forest. So that's good. But if you, that's good because we know that the Breimann algorithm is quite a clever way to handle this kind of diversity. I just noticed that a long time ago, I just read tens of times the paper from machine learning written by Breimann, but I never noticed that there is a small derivation, including the diversity identity I've just mentioned at the beginning of this talk. Just a private joke about Breimann. Everything is in Breimann, in fact. Just kidding. So we obtained the best result for the random forest, but if you inspect the blue line, you can see that the relative improvement is far more important for the purely random forest than random forest. So the intuition that purely random forest can generate more diversity is in fact the good one. We can have zoom in on this diversity term. So you have on this graph in x-axis always the number of iteration of the boosting, but you have here something which is quite different. It's a diversity term. So it is the difference between the so it is written, it is quite clear. This is the mean value. It is the counterpart of the diversity term I add in the cost function. And we have in solid line the diversity term and as a function of the number of iteration in solid line for the purely random forest and in dotted line for the random forest. So you can see that the purely random forest allows to generate more diversities than random forest. It's extremely clear. And you have here the scheme for the classical boosting. So you have something which is diversity increase quickly with M before decreasing slowly with the increase of kappa. So just an example on an electricity consumption data. We start all this stuff. The seminal work we have in common was on forecasting electricity consumption on one hand, and on the other hand, aspect with forecasting pollution data. So just take an example here, with the French electricity consumption provided by RTE, 10 years, something like 10 years, 9 years of observation with half an hour sampling period, with classical covariates. So the X include some lagged value of Y, some lagged value of electricity, and some calendar variable. And we had another covariate, which of course it is quite important, especially in France, that is national average temperature for the French weather forecast Météo France. So we do exactly the same job as usual. We train the model on historical data for the first years, and then use the test set. You use the last year as test set. So I quickly, because I don't know, I am quite running out of time, I think. So I don't know.
Don't worry, don't worry.
Okay,
okay.
Thank you very much, Maria. So essentially, you will see that on this example, we have just confirmation. So we start with random forest as base learner. So we have in blue the F and F star, always the same. F is usual boosting estimate, diversity boosting estimate, and F star is the mean value of that, the average value of that, as a function of kappa. So you can see that the best error are obtained for F and then F star. So it's quite natural to imagine that it's better to take the additive formulation of the gradient boosting algorithm. And it is the same when the diversity is included, followed by the mean value. And this confirms that if you take kappa close to 1, you improve forecasting performance, that you increase the possibility, you push the kappa value close to 1. So you need to be less than 1, less than something which is around 1 to prevent explosion. But you have, it seems that on this illustrative example that you have an interest to increase the diversity parameter. Now, if I just here take the example of the result we obtain with random forest, we can just now check that when you use the poorly random forest, you get more diversity. So if you inspect this graph, you obtain the confirmation that the fact that you have interest to give this additional way of diversifiability, which I don't think that this term exists, but everyone have an idea of the meaning. And just to conclude about this thing, of course, it seems to be quite attractive, but of course we have in mind some question, because it is quite natural to imagine that in some example, if you push diversity, you could increase the performance to get some final estimate which beats the boosting one. That diversity boosting is better than usual boosting. But we decided to do something more. So we have considered one simulated example just to try to understand what is the behavior of the kappa with respect to what we know usually about M and about delta, the usual boosting parameter. We have confirmed this on a data set which is close to what we have in mind in the future application, but we want to take also some benchmark data set of various origin in order to check that even if, of course, the idea is not to beat every time boosting, but to verify that when you use diversity boosting with a quite high value of kappa, you cannot deteriorate, you cannot degrade the performance. So we have considered some well-known benchmark data set. We have here the number of observation, here the number of explanatory variable, and the package, the R package, from which you can retrieve the values of that. So this is the median of root mean square error of the different learners: stump, carp trees, purely random forest, and random forest. And for each base learner, we have just boosted the algorithm. So you start with the base learner stump and you consider boosting stumps, and you consider boosting diversity stumps with a high level of diversity parameter. So we have taken here kappa equal to 0.9. Okay, and then you have in column just the benchmark data set. And we just compare this, so it is a huge number of information, quite uninformative. In fact, you can see two different situation data set in green, for which body beats the boosted, and three data set for which it is not the case. The key point is not to organize a fight between boosting and diversity boosting. I just recalled the way to do that. The first is to confirm that in many cases you could improve. It is not completely evident that improving diversity gives you better results in terms of prediction. What is interesting is that it seems to be the case in some situations which are quite different. The second aspect is that when you focus on the case, so three among in this subset of illustrative example, of course, this does not prove anything as usual. When you take benchmark, it does not say nothing deep, but you can make some remark. In fact, here, if you consider, for example, the ozone one, you can say that you can see that in general, except for purely random forest, the result obtained by the boosting is better than the one obtained by diversity boosting with kappa equal to 0.9. But what is interesting is that the deterioration is not massive. So you don't have really a huge risk to hugely deteriorate the same happens for ethers and air quality. So this is quite interesting to notice. If you want to experiment this, we have we provide a CAN package on the CAN R package denoted by body for boosting diversity in regression ensembles, and you have also a companion site which is maintained by Yannick Good, and you have the script generating all the plots, all the numerical experiment, and then you can experiment your own example. These very simple ideas. So some perspective just to open the discussion. Of course, we could imagine to enlarge the family of base learner. What we have in mind initially is not to consider only a combination of unbiased base learner. So in general, when you consider some method, And when you combine method, you can use convex combination of method if you use some predictors which are all unbiased. But of course, if now you imagine that you have some biased experts, for example, expert with overestimating the values, we have this when you combine some model which are deterministic and some model which are statistical one. In general, the first are flat, for example, in pollution data and in cities, and the other one I quite overestimate. So it could be of interest to consider some bias expert. So that is one way to take. The second way is to estimate the boosting diversity algorithm from the theoretical viewpoint and to try to, for example, obtain some kind of result in terms of statistical optimality. And the key point I just mentioned in my first example, to explore ensemble strategy, different scenario in Meteo, or different tuning parameter on initialization, in optimization, also to have some mechanism. In fact, the seminal discussion about this work was something, we have a project, and the title was The Different Way to Generate Diversity in Predictors. So it is only one piece of a big picture. So the perspective is to try to have some piece of this patchwork. So thank you very much for your attention.
Thank you very much, Jean-Michel, for this nice talk. Very interesting, your very interesting work.